Survey of Calculus, Chapter 4, Section 2, Antiderivatives as Areas. Integral calculus studies the accumulation of units as the input variable increases. In other words, we're studying how something is building up over another variable, like over time. For example, let's say a jogger maintains a constant velocity of 5 miles per hour. As he or she runs, he or she accumulates distance. After 1 hour, 5 miles. After 2 hours, 10 miles. 3 hours, 15, and so on. So they're building up the distance the longer they run. In other words, we're interested in how much of something has built up as a certain variable has increased in value. How much money have we built up as time has gone on, for example. All right, let's look at an example. Emma's motor scooter travels 15 miles an hour for 2 hours. How far has she traveled? Greenleaf Skateboards determines that for the first 50 skateboards produced, its cost is $40 per skateboard. What's the total cost to produce 50 skateboards? Now, these are probably pretty easy, so if you pause the recording, see if you can come up with an answer and then resume. We'll talk about the answer and a way of looking at these problems. So pause the recording for a second and try these. Okay, so for A, her velocity is 15. Now, what you probably did is you said, well, she's gone for 2 hours, 15 miles an hour, it's 30 miles. And that is absolutely perfectly true. But what we're going to do, and it's going to seem weird because you're like, why are we doing it this way? Just bear with me and trust me for a minute. We're going to look at velocity as a function. V of t equals 15, and it's constant. We're going to graph it. It would just be a horizontal line. Okay, so you see that here. You see the line where y equals 15. And we're going to graph it for the x values from 0 to 2. And you see we've cut it off at 2. Now notice something there. That shaded area is a rectangle. Okay? And it just so happens that the answer you got when you said, well, 15 times 2, 15 miles an hour for 2 hours, is 30. That happens to be the area of that rectangle. Okay? So the time that's accumulated that you just kind of quickly calculated is the same as the accumulation of time, is the same as the area of the rectangle. It's the area under the function v of t equals 15 from 0 for x or time to 2. Okay? It's the area under that graph. Okay, the marginal cost is 40. So let's see, we graph c prime of x to obtain a rectangle that measures 50 units by 40 units. In other words, our function is c prime of x is 40. It's cost per skateboard. And we're going to graph that. So it's going to be a horizontal line. And it's going to go from 0 to 50. And the rectangle that's formed when we graph it for that length of x, the area is 2,000. And you probably already figured that out. Well, if it's $40 per skateboard and they're making 50 skateboards, it must be $2,000. Notice that that is the same as the area under the graph. Now let's try another one. It costs Berglund Bakeries 85 cents to produce 1 dozen cinnamon rolls. Find the total cost of production of 10 cinnamon rolls. And what I want you to do is now, seeing how we did the last two, sketch a graph for it. Our function, our cost function, c of t, is 0.85 t times the number of cinnamon rolls, right? So pause the recording, give it a try, and resume to check your answer. Okay, so 0.85, there's the function, and it's going from 0 to 10, and we get $8.50. Again, the cost for 10 is the same as the area under the curve. For linear functions, 2 geometry formulas are going to be very useful, and what we've just been talking about and doing. The first we've already seen, and that's the area of a rectangle, which is base times height. The second that's very helpful is the area of a triangle, and just to remind you, that's 1/2 times base times height. And I bring that up in order to try this problem. The velocity of a model helicopter is given by v of t equals 3t. Now there's our function. T is in seconds, v of t is in feet per second. Use geometry to find the distance. So what you're going to do is you are going to graph the line, v of t equals 3t, and we're going to find the area under that graph from 3 to 5 for t. And let's pause the recording, give it a try, and resume to check your answer. Okay. Here's our graph. Now you might say, well, that's a trapezoid, and it is. And you can, if you remember the formula for trapezoid, you can use it. What they did is they split it into a rectangle and a triangle. Now, knowing what we know about the solution of the function being the area under the curve between the beginning and the ending point, we can figure out the area. The area of the rectangle is going to be 2 times 9, which is 18. And the area under the triangle is going to be 2 times 9 or 2 times 6 times 1/2, which is going to be 6. So 18 plus 6 is 24. Try another one. Causland Incorporated has a marginal profit function, P prime of t equals 0.15 t, where t is in months and P prime of t is in thousands of dollars per month. Graph the function and determine the total profit earned in 1 year. So you're going to graph the function and figure the area under that graph between 0 and 12. Pause the recording, give it a try, resume to check your answer. Okay, we have a triangle this time. And so the base is 12 and the height is 1.8. So 1/2 times 12 times 1.8 gives us $10.8 thousand, or $10,800. All right, just a couple more here. Pause the recording, give these quick checks a try, and resume to check your answer. Now, notice in example 1, to find the distance traveled in a given amount of time when the velocity was 15, we found the rectangular area under the line using A equals 15 times t. Also notice that just so happens to be the antiderivative of the velocity. If v of t is 15, 15t plus c would be the antiderivative, which is the same as the area, except for the plus c part. Interesting. Now, going back to example 3, to find the total profit from the marginal profit, we did the area under the triangle. Well, the function was 0.15 t. For the triangle, we did 1/2 t times 0.15 t, which is 0.15 over 2t squared, which, interestingly enough, is, without the plus c, is the antiderivative of the marginal profit. So what we see here is a relationship between the area under a graph and the antiderivative, and it is not. It's always going to be a pattern that holds true. The antiderivative or integral of a function is the area under the curve that has been generated by that function. Now, in case you're wondering, because so far we've just done these straight line shapes, how in the world would you do this with, what if it was a sine curve or x squared, parabola or cube? How in the world would you do this when you you don't have triangles and rectangles? Well, we don't need to go into great detail about that, but just to satisfy your curiosity, and you do not need to know this or to be able to repeat this back, but just in case you're wondering, if you were taking a Cal 1 course, what you would do is you would take the region, there we go, under the curve. You see here, there's our curve, F is our curve, and what you would do is you would divide it up, divide the length of the distance from A to B up into segments, and you would build triangles off of rectangles off of those segments, as you see here colored in yellow. And you would find the area of these rectangles and you would add all that together. Now, you might wonder, well, yeah, but sometimes they go over and sometimes they're not big enough. And this is true, and it tends to kind of compensate for itself. if you take a Cal 1 course, it goes into a lot more detail because it's more than just simply dividing it into rectangles. It's also where do you touch the top of the curve with the top of the rectangle. There's other things that go into it as well. But as you can imagine, another aspect of this is that the narrower those sections are, the narrower the rectangles are, the more accurate your answer is going to be. So all of that would play into it. And again, if you were taking a Cal 1 course, you would learn all about this, and you'd also learn how to divide it. You'd move from rectangles to dividing it into trapezoids, and then even into kind of some weird regions with curves at the top. We're going to avoid all that. We're just going to go straight into the understanding that the area under the curve can be found by the integral. Like I said, in a full-blown calculus course, you would go through the whole process of coming up with that fact. We're just going to skip right to the fact and not worry about the process, not worry about how to do all the steps in between. So if you need to find the area under the curve, which is an accumulated value, you need to take the integral. So here's just the definition that tells us that. Don't worry about the summation notation. It says let f of x be continuous and non-negative, positive, over an interval from a to b. A definite integral is the limit, and again, this is the summation notation. It's the limit as n goes to infinity or as delta x goes to 0 of the Riemann sums of the areas of the rectangles under the graph y equals f of x over ab. All you need to understand from that is that you're going to take the integral and you're going to take it from starting point A, which is the number on the lower part of the little symbol, to ending point B. We're going to explore more about this in future sections, but that's what you need to know for right now. We're going to graph the functions for what we're doing in this section. You're going to keep doing what we've been doing. You're going to graph the functions and you're going to use geometric formulas, okay? So, find the value. Again, graph the function, it will make a shape. Use geometry, geometric area formulas to find the area. Pause the recording, give this a try, and resume to check your answer. Sorry about that, I brought the graph in kind of late. It is a trapezoid, and you could have used a trapezoid or you could have broken it into a rectangle and a triangle. Either way is fine. Either way you do it, you should get an area of 10. Watch how they've numbered here, be careful. Okay, so the area under the curve can be interpreted as an accumulation of small units of area. We can use geometry to find that, and you see how the definite integral is written. Remember, when you don't have a number at the top and bottom of the symbol, that is called an indefinite integral. Okay, the rest of this is a little bit of additional practice, so pause the recording in between these, try the problems out, resume to check your answer.